Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine looking into a kindergarten classroom. You'd expect to see, 4-year-olds playing with blocks, figuring out basic shapes, just sort of...
napping, spilling juice.
Right, exactly, just starting to piece the world together. But instead, sitting right there in one of those tiny plastic chairs is a fully grown 50-year-old adult.
Wearing a tailored suit.
Doing complex calculus. I mean, it makes absolutely no sense, right? The timeline is just completely broken.
Yeah, that adult simply hasn't had the time to grow up in that environment.
Exactly. And that feeling of just complete paradigm-breaking confusion, that is exactly what astrophysicists experienced recently.
Oh, absolutely.
When the James Webb Space Telescope stared into the deepest, oldest reaches of the universe.
It is honestly the ultimate cosmic anachronism.
Yeah.
We're looking at a stage in the universe's history where everything should be in its infancy.
Right.
Small gas clouds, the very first rudimentary stars just beginning to ignite, small structures starting to merge together.
Just babies. Yeah.
But sitting right there in the middle of this cosmic kindergarten is an absolute monster, a supermassive black hole.
It's wild. And to really understand why this discovery is keeping cosmologists awake at night, we kind of have to look at the classical rules of the universe.
Right, the established playbook.
Right, because the model we've all accepted for decades, it's built on a very simple, very logical sequence of events. You start small.
You have to.
Right. In the beginning, you have giant clouds of gas. Gravity pulls that gas together until it ignites, and boom, you get a star.
Right, and a massive star burns furiously, runs out of nuclear fuel, and eventually, it collapses under its own immense weight.
And that collapse creates a stellar mass black hole.
Right,
Yeah.
exactly. The dead remnant of a single star.
Just a small baby black hole. And from there, the classical model says this little black hole starts to feed. It pulls in surrounding gas as well as rogue planets. Maybe it merges with another small black hole nearby.
It's a slow process of accretion.
Accretion, right. But here's the critical part for you listening. There is a hard physical speed limit on how fast a black hole can actually eat, isn't there?
Yes, the Eddington limit. And this is a crucial piece of the physics puzzle that makes this new discovery just so baffling.
Break that down for us.
So when gas falls into a black hole, it doesn't just drop straight in. It swirls around, like water circling a drain.
Right, forming that accretion disk.
Exactly. And as all that material rubs together at near the speed of light, the friction heats the gas up to millions of degrees.
Oh, wow.
Yeah, and that causes it to emit massive amounts of radiation, just blinding light and heat.
And that radiation pushes outward, doesn't it?
Precisely. The outward pressure of the radiation pushes against the inward pull of the black hole's gravity.
It's a tug of war.
Exactly. So if a black hole tries to eat too much, too fast, the radiation pressure becomes so intense that it actually blows the surrounding food away.
Wait, so it starves itself?
It starves itself. So because of this Eddington limit, a black hole can only grow at a strictly regulated, very incremental pace.
Okay, so to go from a single dead star to a supermassive black hole with the mass of millions of suns.
You need billions of years of slow, steady feeding.
Billions, which means the galaxy, the stars, the gas, the whole food source has to exist first.
Right. The stars are the bricks. You need generations of them, living, dying, and feeding the center to slowly build this supermassive skyscraper.
But the James Webb Space Telescope just found a skyscraper that exists before the bricks were ever even manufactured.
Yeah, it's mind-bending. The object we are looking at is officially cataloged as Abell 2744 QS01.
Okay, let's pause on that name for a second. QS01. I know astronomers love their acronyms, but what does QSO actually stand for, and why does it matter here?
Right, so QSO stands for quasi-stellar object, which is the formal term for what we more commonly call a quasar.
Quasar.
Yeah. When astronomers first discovered these things back in the mid-20th century, they looked through their telescopes and saw what looked like ordinary single stars.
Just little pinpricks of light.
Exactly. But when they analyzed the light, the energy output was impossibly high for a single star. So they called them quasi-stellar.
Quasi-stellar. So they weren't stars at all.
Not at all. It took years to realize that these were actually the intensely glowing accretion disks of supermassive black holes.
At the centers of distant galaxies?
Yes. Feeding so voraciously that they outshine the hundreds of billions of stars in their host galaxy combined.
That is just terrible. So when we talk about QS01, we are talking about an actively feeding, brilliantly bright black hole.
Right. And it's often referred to in the research as little red dot.
Little red dot, which sounds cute, but perfectly describes how it appears on the James Webb imaging sensors.
It does, but that simple visual description really belies an astonishing reality.
Yeah, let's look at the timeline. QS01 existed just 700 million years after the Big Bang. Now, if you're listening to this, you probably know the universe is roughly 13.8 billion years old.
Give or take, yeah.
So let's map that onto a human lifespan to make it visceral. If the universe is an 80-year-old person today, we are looking at a snapshot from when that person was just 4 years old.
A toddler.
A toddler. And at that toddler stage, the light from this object began its journey.
Right. It has been traveling through the expanding vacuum of space for over 13 billion years just to hit the golden mirrors of our telescope.
Which is crazy to think about.
And because the universe is expanding, the space between us and QS01 has been literally stretching the entire time that light was in transit.
Right, which is exactly why we need James Webb in the first place, isn't it? Like, Hubble couldn't have spotted this.
No, Hubble is an incredibly powerful optical and ultraviolet telescope.
Yeah.
But think about what happens when you stretch a light wave.
It changes color.
Exactly. As the universe expands, it grabs the visible light emitted by QS01 13 billion years ago and stretches the wavelength.
So by the time it reaches us,
that wave has been stretched out of the visible spectrum entirely and into the infrared. It's called cosmological redshift.
Redshift. So the light literally becomes redder and then completely invisible to human eyes.
Right. And James Webb was specifically engineered with near-infrared and mid-infrared sensors to capture this exact kind of ancient stretched light.
Okay, so Webb spots this infrared little red dot, but the physical size of this thing is what really caught my attention.
Oh, it's tiny.
It's only 1,300 light years across. For anyone trying to visualize that, our own Milky Way galaxy is about 100,000 light years from edge to edge.
Right.
So QS01 is barely more than 1% the size of our galaxy.
It is incredibly compact.
But wait, if you're listening to this and running the mental math, a massive red flag should be going up right now.
It should.
Because if something is only 1,300 light years wide and it is located 13 billion light years away, it shouldn't just be a dot.
No.
It should be submicroscopic. I mean, it should be entirely invisible, even to James Webb. The resolution required to see any internal structure of an object that small at that distance, it borders on science fiction.
It really does.
How are we not just seeing a single blurry pixel?
Well, that skepticism is entirely warranted. I mean, if we were just pointing James Webb at an empty patch of space and zooming in, we would not be able to resolve the details of QS01.
The optics just wouldn't allow it.
The geometry of the optics simply wouldn't allow it, yeah. We're only able to study this object because we had help from one of the most bizarre and powerful phenomena in physics.
Gravitational lensing.
Exactly. In this case, nature provided us with a giant magnifying glass called Able 2744, also known as Pandora's cluster.
Pandora's cluster, it's like a massive pileup of multiple galaxy clusters. But how does a cluster of galaxies act as a magnifying glass? We're obviously not talking about glass lenses here.
No, we have to step into Einstein's general theory of relativity for this.
Okay, let's do it.
So, Einstein revolutionized our understanding of gravity by showing that it isn't just, a magnetic-like pull between objects. Mass actually bends the fabric of space and time itself.
Right. The classic analogy is the bowling ball on a trampoline.
Yeah, the heavy ball creates a deep dip in the fabric, and if you roll a marble nearby, its path curves down into the dip.
The trampoline analogy is great for picturing the dip, but, and correct me if I'm wrong, light doesn't roll. Light always travels in a perfectly straight line, right? That's a fundamental rule of the universe.
Well, light does travel in a straight line. But what happens when the space it's traveling through is curved?
Oh.
Imagine drawing a straight line on a flat piece of paper. Now, crumple that paper or wrap it around a sphere.
The line you drew is still straight relative to the surface of the paper.
Exactly. But in three-dimensional space, it's bending and curving along with the paper.
Okay, that makes sense. So the light from our little red dot, QS01, is speeding toward Earth. But sitting directly between us and QS01 is Pandora's cluster.
And Pandora's cluster contains the mass of trillions of stars, massive amounts of gas, and just vast halos of dark matter. It is a gravitational heavyweight.
So it's a huge bowling ball on the trampoline.
Huge. It warps the space around it so severely that when the light from QSO-1 approaches, it's forced to travel through this warped, curved space. The cluster essentially pinches the light paths together, focusing them toward us.
Just like a literal magnifying glass focuses sunlight.
Exactly like that.
It concentrates the light, making QSO-1 appear much brighter and larger than it actually is.
But gravitational lenses are not polished glass. They are lumpy, chaotic, and uneven because the mass in a galaxy cluster isn't distributed perfectly.
Right, it's clumpy.
Very clumpy. And this leads to a fascinating side effect. The light from QSO-1 doesn't just take one curved path around the cluster, it takes multiple paths.
Wait, really?
Yeah, some light goes left around a particularly dense pocket of dark matter, some light goes right, some goes over the top.
And because space is warped differently on the left side than the right side, those paths are different lengths.
Exactly.
Yeah.
The light taking the left path might arrive at Earth years before the light taking the right path.
Wow.
And from our perspective on Earth, looking back at the cluster, we don't just see one magnified little red dot. We see three distinct, separate images of QSO-1 smeared across different parts of the sky.
See, I have to play the skeptic again here. Seeing three distorted, smeared copies of a galaxy scattered around a cluster, that sounds like an absolute nightmare for a data scientist.
Oh, it's incredibly complex.
It's literally a funhouse mirror. If you look at yourself in a funhouse mirror, your head is huge, your legs are tiny, your waist is warped. You can't use that reflection to accurately measure your height or your weight.
Right.
So if QSO-1 is distorted by this cosmic funhouse mirror, how can we possibly trust any measurements we take of it?
Well, that is the paradox of gravitational lensing. The spatial image, the physical shape we see on the screen, is absolutely distorted. If we tried to measure its exact physical boundaries based purely on the picture, we'd be completely wrong.
Yeah.
But we aren't just taking photographs. We're taking spectra. And while the funhouse mirror changes the shape of the image, it does not change the fundamental properties of the light itself.
Oh, I see.
Yeah. The wavelengths of light, the chemical fingerprints embedded in that light, the velocity signatures, those remain pristine.
Okay, so the funhouse mirror might stretch my face, but it doesn't change the color of my eyes.
Precisely. And more importantly, the magnification effect, the sheer brightening of the object, is what gives us enough raw photons, enough actual light particles to feed into our most advanced instruments.
So we need the distortion.
We do.
Oh.
Without the funhouse mirror, the light from QSO-1 would just be too faint to analyze. The distortion is the price of admission for the magnification.
And the instrument that paid that price of admission, the one that actually decoded this light, is the near-infrared spectrograph on James Webb.
Yes, the NIR spec.
Specifically using something called an integral field unit, or IFU. I think it's worth taking a moment to explain how this piece of technology works, because it's really the key to this entire discovery. This isn't just a camera.
No, not at all. A standard camera gives you a two-dimensional picture. You see a glowing dot, and you can measure how bright it is and maybe its general color.
Right.
A spectrograph, on the other hand, takes the light from a single point and passes it through a prism, or a diffraction grating, splitting it into a rainbow.
Just like Pink Floyd's Dark Side of the Moon album cover.
Exactly like that. And when you look at that rainbow, you see dark bands or bright lines at very specific colors. Those lines are chemical fingerprints.
Fingerprints?
Yeah. Every element in the universe, hydrogen, oxygen, carbon, absorbs and emits light at incredibly specific, unique wavelengths. By looking at the barcode of lines in the spectrum, we know exactly what an object is made of without ever having to go there.
But the integral field unit, the IFU, takes this a step further, doesn't it? It doesn't just take one spectrum of the whole object.
No, the IFU is an engineering marvel. It takes the image of QSO-1 and slices it up into a grid of hundreds of tiny individual pixels.
Okay.
And then it takes complete separate spectrum for every single one of those pixels simultaneously.
Wait, simultaneously? So instead of just saying, this whole dot is made of hydrogen, the IFU can say, the top left corner has this chemical makeup, the bottom right has this makeup, and the center has this makeup.
Precisely. It's a 3D data cube. You get an X and Y axis for the picture and a Z axis for the chemistry of every microscopic piece of the picture.
That is unbelievable.
And chemistry isn't all the spectrum tells us. The spectrum also reveals motion. And this is how the researchers, led by scientists like Ignace George Babalis and Cosimo Marcancini, this is how they achieved the impossible.
They directly weighed the black hole.
They did.
Okay, we mentioned earlier that we measure motion using the Doppler effect. Let's make sure the mechanics of that are crystal clear for everyone listening.
Sure. Most people experience the Doppler effect with sound. You hear an ambulance coming down the street towards you. As it moves towards you, it's chasing its own sound waves, compressing them. Compressed sound waves mean a higher pitch.
But the moment it passes you...
Exactly. The moment it passes you and drives away, the sound waves are stretched out, and the pitch drops instantly.
And light does the exact same thing, because light is a wave.
Yes. If a cloud of glowing hydrogen gas in QSO1 is moving toward Earth, its light waves are compressed. In the spectrum of light, shorter compressed waves shift toward the blue end of the rainbow.
Which we call blue shift.
Right. And if the gas is moving away from us, the waves stretch out and shift toward the red end of the spectrum. Red shift.
So using the IFU, the researchers looked at the cloud of hydrogen gas swirling around the center of QSO1. Because it's swirling, one side of the gas cloud is naturally coming toward us as it rotates, and the other side is moving away.
Exactly.
The IFU allowed them to look at the left pixel and see a blue shift, and look at the right pixel and see a red shift.
Yes. And by measuring exactly how blue or how red the light was, they could calculate the exact velocity of the gas.
They mapped the speed of a gas cloud 13 billion light years away.
And the map they generated is the smoking gun that destroyed the classical model.
Why?
Because when they plotted the velocity of the gas against its distance from the exact center of the object, they didn't just see a random swirling mess. They saw a highly structured, mathematically perfect curve known as Keplerian motion.
Keplerian motion, named after Johannes Kepler, the astronomer who figured out the laws of planetary motion in our own solar system in the 17th century.
Right.
Let's visualize this because it is the absolute crux of the argument. Think of how our solar system operates. Mercury is the closest planet to the sun. It whips around the sun at blazing speeds.
Very fast.
Venus is further out and it moves slower. Earth is further still, moving slower than Venus. By the time you get out to Neptune, it is practically crawling along its orbit compared to Mercury. The speed drops off in a very specific steep curve the further away you get.
And why does it drop off like that? Because gravity follows an inverse square law. The gravitational pull of the sun weakens drastically as you move outward.
Right.
But the only reason we see this clean, predictable curve in the solar system is because the mass of the solar system is not spread out. Over 99.8% of all the mass in our entire solar system is concentrated in a single, incredibly dense central point.
The sun.
The sun.
I like to picture it like a tetherball pole on a playground. You have a heavy, solid metal pole in the center and a ball attached to a string. When you hit the ball, it swings around the pole in a tight, predictable arc. The tension is clear, the anchor is clear.
Oh, that's a great analogy.
The mass is in the middle, and the gas or the ball simply responds to that central mass.
And that is exactly what the IFU data showed in QSO1. The hydrogen gas closest to the center was moving at blistering speeds, thousands of kilometers per second.
Wow.
And as they measured the gas further out, the velocity dropped on a perfect Keplerian curve. The tetherball pole was there.
But what if it wasn't a black hole? I mean, what if QSO1 was just a really dense cluster of stars, like a normal galaxy in the making?
Well, if QSO1 was a normal, mature galaxy packed with stars, the mass would be distributed. It wouldn't be a tetherball pole.
Okay.
Imagine instead that the mass was a massive, chaotic swarm of bees. If you throw a ball through the swarm of bees, there is no single central anchor pulling on it. It gets pulled a little to the left by this clump of bees, a little to the right by that clump.
So the rotation wouldn't be smooth. Like if you look at the rotation curve of a normal galaxy like the Milky Way, it does not drop off steeply at the edges.
Right.
The stars at the outer edge of our galaxy are moving surprisingly fast. That flat rotation curve is actually how we discovered dark matter, right?
Yeah.
Because there was invisible mass spread throughout the galaxy pulling on the outer stars.
Exactly. A distributed mass creates a flat or chaotic rotation curve. A concentrated mass creates a Keplerian curve. And the data from QSO1 was undeniably Keplerian.
So it's concentrated.
Yes. The gas was governed entirely by the simple laws of gravity acting on a single dominant central mass.
Which meant the team could do something unprecedented. By knowing the velocity of the gas and its distance from the center, they could use basic Newtonian physics to calculate exactly how much mass was required to force the gas to move that fast.
They didn't have to guess. They didn't have to extrapolate from modern black holes. They directly weighed the invisible anchor.
And the number they derived was staggering.
Oh, yeah. 50 million times the mass of our sun.
50 million solar masses. I mean, just let that sink in for a second. Just 700 million years after the Big Bang, an object with the weight of 50 million suns is sitting in the center of this tiny 1,300 light-year wide speck of space.
It's massive.
But as immense as that number is, the sheer mass isn't what breaks the models, is it? The real shock comes when you compare that 50 million to the rest of the object.
Right. This brings us to a terrifying revelation about the structure of QSO1. We can calculate the mass of the black hole from the gas velocity. We can also estimate the mass of the entire system, the gas, the potential dark matter, any faint stars that might be there.
Based on the total light and dynamic motion.
Exactly. And when the researchers compared the two, they found that the black hole makes up at least 2/3 of the entire mass of the object.
66%.
At least. It could be even higher.
The black hole is 2/3 of the whole. To understand why that is so utterly bizarre, we have to look at our own neighborhood. Let's look at the Milky Way. We have a supermassive black hole at the center of our galaxy, Sagittarius A star.
Right.
It's a beast. It's about 4 million times the mass of our sun. But the Milky Way galaxy as a whole, including the hundreds of billions of stars, the sprawling spiral arms of gas, the massive halo of dark matter, the Milky Way weighs something on the order of 1 trillion solar masses.
Which means, mathematically, Sagittarius A star makes up roughly 0.0004% of the Milky Way's total mass.
That's nothing.
In the modern universe, a supermassive black hole, as terrifying and powerful as it is basically a rounding error when you weigh the entire host galaxy.
It's a tiny anchor in a vast ocean of stars. Even in the most extreme giant elliptical galaxies we see today, the central black hole might make up maybe 1% of the host's mass.
If that.
But in QSO1, it is 66%. The proportions are just flipped. It's a lopsided universe.
That is the perfect way to phrase it. This isn't a galaxy that happens to have a black hole in the center. This is a massive black hole that just happens to have a faint, wispy halo of gas clinging to it.
It's essentially a naked supermassive black hole.
Pretty much.
The environment is completely and utterly dominated by this singular gravitational monster, and this profound imbalance is the first major blow to the classical theory. Because if the black hole is built from the remnants of dead stars, where are the rest of the stars?
Yeah. Exactly. A stellar population, large enough to produce enough dead seeds to merge into a 50 million solar mass black hole, should still be there, orbiting around it. The galaxy should outweigh the black hole by orders of magnitude.
And the mystery deepens when we turn our attention back to that wispy halo of gas. The IFU didn't just measure the velocity of gas, it measured the chemistry.
Right.
If there was a massive population of stars that lived, died, and fed this black hole, there should be chemical evidence left behind in the surrounding gas.
And here we need to talk about metallicity. The term metal in astrophysics is frankly confusing for anyone who took high school chemistry.
Yeah, I remember being so confused by this at first.
It's an amusing quirk of the field. To a chemist, a metal is a specific type of element with metallic bonds, like iron, copper, or gold. Oxygen is certainly not a metal. Neon is a noble gas, not a metal.
Right.
But to an astronomer, the periodic table is much, much simpler. There's hydrogen, there is helium, and absolutely everything else on the periodic table is thrown into a single bucket labeled metals.
Which seems lazy, honestly. Why do they do that?
Because of the Big Bang. In the first few minutes after the universe was born, the energy was so intense that subatomic particles fused together to create the very first atoms.
Okay.
But the universe was expanding and cooling rapidly. By the time things cooled down enough for fusion to stop, the universe had only managed to forge 2 elements, hydrogen and helium, with just a microscopic dusting of lithium.
That was it?
That was it. The entire universe was a pristine, chemically boring cloud of hydrogen and helium.
So the primordial universe had 0 metals. No oxygen, no carbon, no iron, no silicon.
Exactly. So where did all the complex elements come from? Where did the carbon in our DNA or the calcium in our bones or the oxygen in our atmosphere originate?
They were forged inside stars.
They were forged inside stars.
A star is fundamentally a nuclear fusion reactor. The crushing gravity of the star pushes inward, squeezing hydrogen atoms together so tightly that they fuse into helium. This releases energy, which pushes outward, keeping the star stable.
But eventually, a massive star runs out of hydrogen in its core. Gravity starts to win, crushing the core even tighter, raising the temperature even higher.
And then what?
Now, it's hot enough to take that helium and fuse it into carbon. Then the carbon fuses into oxygen, then neon, silicon, all the way up to iron. The star becomes an onion. with layers of progressively heavier elements being forged in the crushing heat of the core.
But those elements are locked inside the star. How do they get out into the gas clouds of the galaxy?
When a massive star reaches iron, the fusion process stops releasing energy. It actually absorbs energy.
Oh, that's bad.
Very bad. The outward pressure disappears, and in a fraction of a second, the entire star collapses inward. The core rebounds in an unimaginably violent explosion called a supernova.
Boom.
Boom. That explosion tears the star apart, violently scattering all those newly forged heavy elements, the metals, out into the surrounding interstellar gas.
It pollutes the environment with heavy elements. It's stellar debris.
Yes. So when astronomers look at a gas cloud in our modern Milky Way, they see a high metallicity. They see lots of oxygen, carbon, and iron mixed in with the hydrogen.
Right.
That high metallicity tells them that countless generations of stars have lived, burned, and exploded in this neighborhood over billions of years. The gas is rich with the ashes of dead stars.
Which brings us back to the little red dot. The James Webb Space Telescope looked at the spectrum of the gas swirling around this 50 million solar mass black hole.
It did.
If the classical model is right, and this black hole was built from the collapsing remnants of massive stars, the surrounding gas should be choked with the heavy elements blown off by all those supernovas.
But the data showed almost nothing.
Nothing.
The composition maps revealed that the gas in QS01 is almost entirely pure hydrogen and helium. The metallicity is incredibly low. To put a number on it, the gas around QS01 has less than 0.5% of the metallicity we see in our own sun.
Less than 0.5%. It's virtually pristine.
It is one of the most chemically unpolluted galactic environments ever measured. The complete lack of heavy elements is the definitive smoking gun.
Let's put the puzzle pieces together here because the picture it creates is undeniable. Puzzle piece 1. We have a colossal black hole weighed directly by tracking the Keplerian motion of the gas.
Right.
Puzzle piece 2. The mass ratio is completely lopsided. The black hole dominates the environment, meaning there's no massive galaxy of stars hiding in the dark.
Exactly.
Puzzle piece 3. The gas that is there is pristine hydrogen and helium, proving that no massive generations of stars have lived and died here to create stellar debris.
The conclusion is inescapable. The black hole did not form from stars.
The bricks do not exist, yet the skyscraper is standing.
Yes. The classical model of gradual accretion-based growth from stellar seeds simply cannot explain this object.
So if it didn't come from dead stars and it couldn't have grown slowly over billions of years because of the Eddington limit we talked about earlier, we are left with a massive void in our understanding.
We really are.
How does a 50 million solar mass monster just pop into existence 700 million years after the universe begins?
Well, this discovery has forced astrophysicists to dust off theoretical models that until now were largely considered mathematical curiosities.
Fringe theories.
Basically, yeah. If you can't build a black hole slowly, you have to build it fast. You have to bypass the star phase entirely. The data strongly points to one of two primary mechanisms: primordial black holes or direct collapse black holes.
Okay, let's take these one by one because we are moving into the realm of extreme theoretical physics here.
Definitely.
Primordial black holes. The name suggests they were there at the very beginning. How early are we talking?
We are talking about the first literal fractions of a second after the Big Bang. This mechanism doesn't require gas clouds or stars. It requires the sheer chaotic density of the infant universe.
Okay, picture the universe just microseconds after it popped into existence. It isn't a vast empty vacuum yet. It's incredibly hot, incredibly dense, and incredibly small. All the energy and matter that will ever exist is crammed into a microscopic space.
And in that ultra-dense state, the distribution of matter wasn't perfectly smooth. Because of quantum mechanics, there were microscopic fluctuations. Some tiny microscopic patches of space were just slightly denser than the patches next to them.
Quantum fluctuations, like the static on an old television screen.
Yes. And as the universe underwent inflation, a period of unimaginably rapid expansion in the first fraction of a second, those microscopic quantum fluctuations were stretched out to macroscopic sizes.
Whoa.
Suddenly you have regions of the universe that are significantly denser than others.
And because the universe was still so compressed that extra density was enough to tip the scales, gravity took hold of those dense pockets and crushed them instantly.
Completely bypassing the need for matter to cool down, form gas clouds, and ignite into stars. The sheer ambient pressure of the early universe crushed these pockets directly into black holes.
That's wild.
These are often referred to as heavy seeds. They didn't start with the mass of one star. They could have been born with a mass of thousands or even millions of suns right out of the gate.
Born big. They never had a childhood. They just appeared as massive gravitational sinkholes in the fabric of the young universe. That is mind-blowing.
It is.
But there's a second option on the table. The direct collapse black hole. This happens a little bit later in the timeline, right? When the universe has actually cooled down enough to form massive clouds of hydrogen gas.
Yes, but to understand how a massive cloud directly collapses into a black hole without forming stars first, we have to understand why clouds usually form stars in the first place.
Okay.
It's a thermodynamic battle between gravity and heat.
Let's break that down. You have a massive cloud of primordial hydrogen gas floating in the early universe. Millions of times the mass of the sun. Gravity is constantly pulling all that gas inward, trying to crush it into a single point.
But as gravity pulls the gas inward, the gas compresses. And basic physics tells us that when you compress a gas, it heats up.
Think of a bicycle pump. When you push the plunger down and compress the air, the metal barrel of the pump gets physically hot in your hands.
Exactly. So as the giant gas cloud collapses, it gets intensely hot. The heat generates thermal pressure, which pushes outward, resisting gravity.
It balances out.
Right. If the cloud stays hot, it cannot collapse further. It becomes stable.
So how does a star ever form? If the heat stops the collapse, you just have a hot cloud forever.
In order for gravity to win, the cloud has to get rid of that heat. It has to cool down. It does this by radiating energy out into space. In the modern universe, the heavy elements, the dust and metals, act as incredible cooling agents.
Oh, interesting.
They absorb the kinetic energy of the gas and radiate it away as infrared light. Once the cloud cools down, the thermal pressure drops. Gravity takes over again, and the giant cloud shatters and fragments into thousands of smaller, denser clumps.
And each of those smaller clumps continues to collapse until the pressure ignites nuclear fusion, and boom, you get a cluster of stars.
That is the normal path. But in the primordial universe, as we established, there are no heavy elements to act as coolants.
Right, no metals.
The only thing the cloud can use to cool itself is molecular hydrogen. Two hydrogen atoms bonded together. Molecular hydrogen is a very inefficient coolant, but it does work. Slowly, it radiates heat away, allowing the cloud to fragment and form the very first generation of stars.
Okay, so if the cloud fragments into stars, we don't get our 50 million solar mass black hole. How do we stop the fragmentation? How do we get the direct collapse?
We have to destroy the coolant.
Oh.
Imagine a scenario where one of these massive million solar mass gas clouds is sitting in space. But nearby, maybe relatively close in cosmic terms, a different gas cloud did successfully fragment and form a massive cluster of the very first ultra-bright, super hot early stars.
Those early stars would be blasting the surrounding space with intense ultraviolet radiation.
Intense, blistering UV light.
Yeah.
And that UV light slams into our pristine gas cloud. The radiation is so energetic that it physically breaks the molecular hydrogen bonds apart.
It tears them apart.
It splits the molecules back into single hydrogen atoms.
It destroys the coolant.
Precisely. Without molecular hydrogen, the massive cloud cannot cool down. Because it cannot cool down, it cannot fragment into smaller clumps. It stays as one massive monolithic cloud.
Wow.
But it is still accumulating mass. More and more gas is drawn in. The cloud gets heavier and heavier and heavier.
But the heat is still pushing back. It's a standoff.
It is a standoff until it reaches a critical breaking point. The mass of the cloud crosses a threshold where the gravitational pull simply overwhelms the thermal pressure entirely.
And then?
Because it couldn't fragment, the entire million solar mass cloud violently collapses all at once. It doesn't stop at the star face. It crushes itself with such overwhelming force that it collapses straight into a supermassive black hole. Direct collapse.
It skips the middleman. It goes from a cloud of gas straight to a cosmic monster in one catastrophic event.
Yep. In either scenario, whether it was a primordial heavy seed born from the quantum foam of the Big Bang or a massive gas cloud directly collapsing under the glare of neighboring stars, the conclusion is the same.
They were born big.
These supermassive black holes were born massive. They didn't grow up over billions of years. They arrived on the scene already fully formed.
And what's truly profound to me is that the researchers looking at QS01, they don't think this is a freak anomaly. The James Webb Space Telescope is finding more of these little red dots scattered across the early universe.
Yes, quite a few of them.
If this is a common occurrence, if this is a standard feature of the early cosmos, it completely flips our understanding of how galaxies are built.
It really does. For a century, we assumed that galaxies formed first. The vast clouds of gas fragmented into stars, the stars merged, they died, and eventually, over immense stretches of time, a black hole formed in the center as a byproduct of the galaxy's evolution.
The galaxy built the black hole.
The galaxy built the black hole. But the data from QS01 tells us the exact opposite.
The black hole forms first.
It is born massive, either as a heavy seed or a direct collapse.
Right.
It sits there, a naked gravitational anchor in the dark. And because it is so massive, its immense gravity begins to draw in the surrounding gas from the intergalactic medium. It pulls the raw materials toward itself.
And as that gas falls inward, swirling around the black hole, it eventually cools and fragments in the outer reaches of the halo, finally forming the stars.
Right.
The black hole acts as the heavy gravitational anchor that forces the galaxy to assemble around it. The black hole builds the galaxy.
It's incredible. Think back to the years before James Webb launched, when astronomers were looking at distant, early quasars with less powerful telescopes. They saw the blinding light of these feeding monsters, and they used indirect measurements to estimate their mass.
Oh, I remember this.
And when those indirect measurements suggested black holes weighing billions of solar masses existing just a few 100 million years after the Big Bang, many theorists pushed back.
There was intense skepticism, right?
Huge skepticism. The classical model said it was impossible, so the assumption was that the measurements were wrong. Theorists argued that because we were extrapolating data from modern local black holes and applying it to the early universe, we must be overestimating their mass.
That makes sense.
They assumed the physics of feeding, or the way light escaped the accretion disk, must be fundamentally different in the infant universe, creating an illusion of massive weight.
But the Keplerian motion data, the tetherball test, proves that those early astronomers weren't crazy.
No, they weren't.
The indirect measurements weren't an illusion. We weighed the anchor directly using pure gravity and velocity, and the massive weight is real. It is a total vindication of the observations, but it requires the complete destruction of the theoretical model.
It is the ultimate triumph of observational astronomy. When the data fundamentally contradicts the established theory, you don't throw out the data, you throw out the theory. The universe is telling us how it works, and we just have to listen.
It is a phenomenal story of scientific discovery. Let's take a step back and look at the sheer scope of what we've unpacked today. We started with a fundamental paradox, a chicken and egg problem about the origins of the largest structures in the cosmos.
Right.
We zoomed in on a tiny speck of light, a little red dot, that existed when the universe was just a toddler, a mere 700 million years old.
We saw how the immense gravity of Pandora's cluster warped the very fabric of space, acting as a cosmic funhouse mirror to magnify that ancient light and send it across 13 billion light years to our mirrors.
And by slicing that magnified light into a 3D data cube, capturing the redshift and blue shift of glowing hydrogen, scientists mapped the perfect, predictable Keplerian rotation of gas swirling around an invisible center.
The tetherball test.
They used the tetherball test to directly weigh an object from the dawn of time, revealing a 50 million solar mass Titan.
A Titan that completely dominates its environment, making up over 2/3 of the total mass, surrounded by pristine gas that shows absolutely no trace of the heavy elements that would indicate a history of dying stars.
It is a skyscraper built without bricks. It proves that in the extreme conditions of the infant universe, black holes were born massive, entirely bypassing the slow, gradual evolution we see today.
We didn't just find a weird object. We watched a foundational pillar of classical cosmology crumble.
It forces us to rethink the sequence of events that led to our own existence, which leaves us with a profound, almost unsettling question for you to mull over, one that the scientific community will be wrestling with for decades.
Yeah, it's a big one.
If supermassive black holes formed firstborn from the quantum foam of the Big Bang or the sudden catastrophic collapse of primeval gas clouds, and if they acted as the fundamental anchors that pulled the surrounding universe together to forge stars.
Does that mean every galaxy we see, including our own Milky Way, the very galaxy that houses our solar system, our planet, and us?
Is everything around us just the beautiful, glittering aftermath of a primordial monster born in the first chaotic seconds of time?